you see problem 1F for lesson 1, and this apply the normal and shear stress from a cow member, centric axial loaded member when we cut face that form an angle theta from the transverse. The transverse means perpendicular to the longitudinal axis. And as we already learned, with that cut, the normal stress equal to P over the transverse areas times cosine theta square, where theta is the angle from the transverse. And then tau, the shear stress, equal to P over AT, the transverse area, sine theta and cosine theta. And in this problem, they ask us to plot the equation above with two equations for normal and shear stress, and use the normal force 25 kips and area is 0.785 square inch. And they want us to vary the angle theta, angle of the cut, from 0 degree, which is the transfer cut, to 180 degrees, so it's going down. Go back to the reverse cut and plot the curve both for normal stress sigma and shear stress tau in the same graph. So that kind of problem, it's good we apply your knowledge in computational tools, which is using Excel or MATLAB. And I'm going to show you both, and it's already available on Canvas. So let's talk about the Excel. So you have here the area, and then the normal force P, 25 kips, the area 0.785 square inch. The angle they ask us to vary from 0, which is the transverse, go back to 180, also the transverse going down. And for sine and cosine that you apply in Excel, you need to convert that into the radians. So with that, theta, we can apply the degree times pi over 180 in Excel. You can put 3.14 for the pi, but to be more exact, you can say pi in parentheses, as shown in that equation here. And you see that there. So that can be an equation to find out pi, and we can drag to find theta for all in degree for all of the scenarios. And then we can go ahead to apply the equation for normal stress, which is P over AT cosine theta square, and the shear stress tau is equal to P over A sine theta and cosine theta. And with that, we can drag down to find out the normal stress sigma and tau, shear stress tau in kips per square inch, KSIs, for each of the angle vary from 0 to 180. And from that too, we can drop with the horizontal axis is theta in degree from 0 to 180, and stress vary. And as you can observe from the normal and stress in here, what we can see when we cut the angle theta equals 0, we see the transfer cut, and then go back to 180, also a transfer cut. You see the normal stress is get the maximum, and in this case the maximum is 31.85 KSI. So bottom line, the normal stress will get the maximum when we cut an angle perpendicular to longitudinal axis, or the transfer cut. And at that time, you see the red one, the red line for the shear stress gets 0 when you do the transverse cut. And then it, for the tau, it increasing at 45 degrees, it will get the maximum. And the maximum at the 45 degrees is about 15.92 KSI for the tau. So you see that the tau is increasing and get the maximum at the cut from an angle from the transfer 45 degree. Similarly, at 135 degree, as you can see in here. So that the behavior for the shear stress and normal stress. And normal stress, as you can see, when we cut the angle theta 90 degree, what does 90 degree mean? It means the cut parallel to the longitudinal axis, both normal stress and shear stress equal to 0. So that the behavior that you can see if we wrap it in Excel. And similarly, we can do in we can do in MATLAB code in there. So, and it also available on Canvas. So we set up A equal to 0.785 square inch, B equal to 25 kips, and we vary theta degree with incremental 10, so you can find out the sigma equation P over A cosine theta square. Keep in mind, in MATLAB, we can use the theta, the angle in degree. With that, you can have cosine D, as you can see here, or sine D, if you want to use in degree, without convert that angle into radians. And then we can, after that, we can go ahead to view the plot function in MATLAB for each of them, and define even the line width, define the color, blue, red, so it's same to the Excel. And as you can see, now it's the same in the Excel. The blue is the normal stress sigma in KSIs, and the tau, the shear stress, red, the behavior exactly the same as the one that you see it in Excel. So that conclude for the worksheet 1F solution.